Hey everybody, in case you missed it, this is the first lesson for Chapter 4. It's on roots and powers, but we're actually going to start with a little review of something you were supposed to learn in grade 9, and that's sets of numbers. I like to think of sets of numbers kind of the way I think about these things. Ever seen these things here? They're called nesting dolls or Ukrainian dolls. And the little one fits inside the bigger one, it fits inside the bigger one, fits inside the bigger one. That's the way I think about numbers. The smallest set of numbers, while still being infinite in size, is the set of natural numbers n, which we would define as numbers. The counting numbers don't start at 0. The examples here is the set of numbers 1, 2, 3, 4 to infinity. And the counting numbers don't include 0. You don't need 0 to count with, so 0 is not a counting number. And the reason why you don't need 0 to count is that, well, think of Roman numerals, I. They didn't need 0 to count discrete things. The next set of numbers does have 0, and that's the whole numbers, which is usually symbolized with a W. And that, you could just say, is your counting numbers, including 0. So that would be the set of numbers that we'd call 0, 1, 2, 3, to infinity. So it's really only different by one thing. So notice again, this entire set fits in here. So that's that whole nesting doll analogy. Integers, oddly enough, is symbolized with a Z, capital Z. And integers is whole numbers and their negative opposites. So this is the first set that goes infinite in both directions. So it goes to negative infinity, then negative 3, negative 2, negative 1, 0, 1, 2, 3, oops, I missed 2, 3, and then all the way to positive infinity. Notice that things like negative 1/2 or negative 0.7 are not integers. Integers are still whole amounts. They're still the signposts on the number line and not the things between them. The set that does include the things between them is the rational number set, which we symbolize with the letter Q. And rational numbers would be any number that can be expressed as a ratio, which you could say is also a fraction, of integers. So the more technical definition is that's A over B, where A and B are integers. Oh, and of course B can't be 0 because you can't divide by 0. So that would be everything. Now this is not something where I can list them in order like I did for integers. There is actually a way that you can list every possible rational number in order, but it's pretty complicated and a little beyond the scope of this video. But just to give you some examples, again, it goes to negative infinity, and then things like negative 3.5, because think of that as negative 3.5, negative 1/10, positive 1/4, negative or positive 0.6 repeating. Basically, any fraction or decimal that does one of two things. A decimal has to either end or repeat. As long as the decimal repeats or terminates, there is a way to turn it into a fraction, so it is a rational number. So that leaves us with the opposite of rational numbers, irrational numbers. That's its symbol, a Q with a line over it to negate Q, not Q. That would be any number that can't be expressed as a ratio of integers. And if you want to express it as a decimal, then it's a decimal, so decimals that don't end or repeat. And you've probably encountered a few of these before. Again, oddly enough, this list is an even larger infinity than this list. That's hard to get your head around, but that's the way math works. Some infinities really are bigger than others, and this infinity is infinitely bigger than that infinity. And some of the ones that you've maybe come across is, well, for example, pi is a number like this. Its decimal does not end or repeat. It's irrational. The square root of 2, the square root of 3, the square root of 5, really the square root of anything that is not a perfect square. And then things like, for example, these weird little number patterns maybe you saw back in grade 9 where we'd go 1, 0, 1, 0, 0, 1, 0, 0, 0, 1. I mean, I can see the pattern that's happening, but that's not really repeating. So there's no fraction I could ever give you that when you divide it out, you would get this pattern for its decimal. Fractions don't behave that way, so a pattern like this would be an irrational number. Now, all of the above, notice that these guys here, the rational numbers, include the integers, which includes the whole numbers, which includes the natural numbers. If you're wondering how the rational numbers includes the integers, well, you can think of all these numbers as, for example, -3 over 1. There you go. -3 is a fraction. All of the integers are fractions. And then if you group together these numbers plus those numbers all together, all of these things exist on the number line, and we call that, of course, the real number line. So the real numbers is all of the above. It's the biggest of the Ukrainian nesting dolls that has everything else inside of it. So any number that you can find on a number line. And that's the way I think about it as a Venn diagram right there. The natural numbers, so that'd be 1, 2, 3, 0 goes in here. All your negatives, -1, -2, -3 go here. All of your fractions and decimals that I can say terminate or repeat and turn into fractions, they all go there. And then all my irrational numbers go here, but the whole group is contained in what we call the set of real numbers. So that's the types of numbers that you're supposed to be familiar with from grade 9. So that was just a little review of that. Now we're going to get started on just a few examples here and determine whether each number is rational or irrational. And again, I'll denote rational with a Q and irrational with a not Q. So -15 is definitely rational because I can express it as -15 over 1, right? A fraction of two integers. 1.21 is like saying 1 and 21 hundredths, which is like saying 121 hundredths, so that's definitely a ratio of two integers. Now the square root of 100, 100 is a perfect square, so that's 10 over 1, and once again, we're looking at a rational number. 6/11 is literally the ratio of 6 to 11, so that's definitely a rational number. Now this might make you think it's irrational, but look at it closely. 49 is a perfect square, and 16 is a perfect square, and that is a ratio of whole numbers. So in the Sesame Street game here, one of these things is not like the others. This is the odd one out. This is the square root of 18, which if I wanted to expand it as a decimal on my calculator, I'd get 4.246, 2.42640, and that would never end, and it would never make a pattern that repeats. So the square root of 18 is definitely irrational. Okay, something else that you learned how to do back in grade 9, hopefully, was comparing all these different types of numbers and putting them on a number line. To make my life easier, I'm just going to label them A, B, C, D, and E, and I'd like to find out where those numbers go on my number line. So let's see. The square root of 23 is an irrational decimal because 23 is not a perfect square, so it's something like 4.8 roughly. So the square root of 23 is around 4.8, so that's going to be, say about there. So there's A. Okay, the square root of 9 is a whole number. It's 3. So that's right there. So there's B. Negative 5 over 2. Okay, let's think about that. Well, that's like saying negative 2 and 1/2, or if you like decimals better, negative 2.5. So that'd be over right in the middle there. So there's C. The D one, the cube root of 28. Okay, well, is 28 a perfect cube? Well, let's see. 1 times 1 times 1, no. 2 times 2 times 2 is 8. 3 times 3 times 3, ooh, is close as 27. But if I go to 4 times 4 times 4, I pass 28. So 28 cube rooted would definitely be an irrational number. If you've never found cube root on your calculator before, pretty much every scientific calculator has it. On this one, you can see right there. I don't know if you can see that. I guess barely. It is the second function of the cube button. So if I cube root 28, again, I get a decimal. It doesn't end, doesn't repeat. So roughly 3.04 if I rounded it. So 3.04 approximately. So that's going to be pretty close to here. So close it'd be actually hard to tell apart, but it's definitely to the right of it. So the B one's on the left, and what one was this? This was D. The D one's on the right. And then that leaves me with this number here, 2.3 repeating, well, or negative 2.3 repeating. Well, negative 2.3 repeating is rational because it's negative 2 and 1/3, also known, of course, as 2 times 3 plus 1, negative 7/3. So on the number line, negative 2 and 1/3, careful, that's negative 2, well, that's negative 2.5, so negative 2 and 1/3 might be about there. So there we go. That's example 2. All of those numbers are in those little homes on the number line. That's where they live, on the number line. Okay. Moving into lesson 4.3, because 4.2 was pretty short, as you saw. We're going to take a look at mixed and entire radicals. Now, you already saw me kind of deal with radicals a second ago when I talked about square rooting. The square root is a radical. The cube root that you saw me play with a minute ago is also a radical. Think of a radical as any a number under a root sign, or for example, a nth root. Those would be radicals. And radicals have actual parts. In fact, I could say that if I have n root a, the a is what we call the radicand. The actual square root bracket is the thing that we actually call the radical. And if you ever wondered what the little number here is, if it's a cube root or whatever, this is what you call the index of your root. So those words might get bopped around a little bit this unit, so try to get used to them. And of course, they don't always have to look like that. You could have something like the square root of 16. If I have the square root of 16, which you know to be 4, remember that this square root sign also kind of says, hey, what number times itself makes 16? Hopefully you'd know that that's a 4. And you can actually know that when you're using a square root radical, you know that the index is 2, but we never bother to write it down. Kind of like in algebra when you write x, you never bother to say that that's 1x, but that's exactly what you mean. So that's me trying to draw an arrow. Sorry, guys. So the square root index, that missing number that you don't see there, is really a 2. But if I had something like cube root of 8, which is a 2, well, the 3 is my index. And this asks the question, hey, what number times itself 3 times is 8? And the answer to that is 2, because 2 times 2 times 2 makes 8. Get it? There is 3 of them. And in case you've forgotten, that is how radicals work. And if you say something like, for example, cube root of x minus 4, you would say then, in words, this would be the, oops, that's a C, cube root of x minus 4. And that's how you say it. This I would say as the square root. So there's just a quick basic breakdown of radicals in case you kind of forgot how they work. And radicals have a rule, a multiplication property, if you will, that says that the square root of a times the square root of b is equal to the square root of a times b. What that means is that if you're taking the same type of root, if they're both square roots or they're both cube roots, you can combine a multiply as actually multiplying the radicands together under one radical. An example with numbers would be that the square root of 4 times the square root of 5 is actually the square root of 20. And if you don't believe it, we can actually prove it here. The square root of 4 times the square root of 5 is about 4.47 and change. If I take the square root of 20, I get the exact same decimal. So yep, that is an actual rule that we can use, the multiplication property of radicals. Now, that rule working backwards allows me to simplify radicals. Here's what we mean by simplifying radicals. A mathematician doesn't consider the square root of 48 to be simplified. Kind of like if you think back to when you learned fractions, just an aside here, 2 over 4 is not considered to be simplified by a mathematician because it can be simplified to 1/2. Or, for example, 4/16 can be simplified to 1/4. A mathematician likes their fractions in simplest terms. The same thing is true for radicals. You see, the square root of 48, well, it might be useful to kind of have off to the side somewhere a list of your perfect squares. My perfect squares are 1, because that's 1 times 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. There's our first 10. We'll stop there for now, but it's actually nice if you know them all the way to 20. Those are my perfect squares. What are my perfect cubes? That's me trying to draw a cube. Well, 1 is still a perfect cube because it's 1 times 1 times 1, but 2 times 2 times 2 is 8, then 27, then 4 times 4 times 4 is 64, then 125, 6 times 6 times 6 is 216, 7 times 7 times 7 is 343, 8 times 8 times 8 is 512, 9 times 9 times 9 is 729, and 10 times 10 times 10 is 1,000, of course. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's helpful to kind of have those numbers in your memory banks. It's nice to kind of memorize these if you haven't already. And again, it might be also nice if you kind of kept this going to, 121, 144, 169, 196, etc. It'd be nice if you could go all the way to 400. I'll leave that up to you to figure all that out. And again, nice to have it memorized. Okay, so we're going to keep those numbers handy. Which of those numbers from this perfect square list did you notice in 48? And you're probably going, well, wait a minute, there was a 4, but there's actually a bigger number than that. What's the biggest perfect square? Because again, think back to fractions. If I had 4 over 16 and I said, oh, I'm going to simplify that, it simplifies to 2 over 8. Well, a mathematician would say, well, keep going. You only divided top and bottom by 2 when you could have divided top and bottom by 4. Haha, that's more simple than that. So, the fact that there's a 4 in here doesn't excite me, but the fact that there is a 16 in it, well, that is something I can simplify. That's going to become 4 root 3. What the heck happened there? Well, I actually use this rule kind of backwards. I think of square root of 16 times square root of 3 as the square root of 16 times the square root of 3. Now, the square root of 3 is, again, an irrational decimal. I don't even know what it is. 1.7 something? Yeah, there it is. 1.73 blah, 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 blah. But the square root of 16 is 4. So this kind of looks more complicated, maybe, 4 root 3 versus root 48. But to a mathematician, this is simplified. We think this is simpler than that, the same way that we think a quarter is simpler than 4/16. So that's what you have to do when you're simplifying a radical. Okay, let's try a couple more. How about the square root of 40? Well, what's the biggest perfect? You got it? This is 4 times 10, so this is 2, or square root of 4, well, maybe I should do this in 2 steps. Square root of 4 times the square root of 10, which is 2 root 10. And that's the way you'd say it too, 2 root 10. You don't have to say times, we know that's a times. Just like every time you say 2x, you mean 2 times x. You don't always say 2 times x, you just call it 2x. And by the same token, we call that 2 root 10. Let's try 72. Well, there's a 9 in it. 9's a perfect square, but think bigger. 4 is a perfect square too. So you know what the biggest perfect square in this number is? What's 4 times 9? The biggest perfect square is 36. So this is 36 times 2, which is the root of 36, times the root of 2, which is 6 root 2. Okay. Moving right along. Let's simplify one that's a little bit more difficult. What's the biggest perfect cube in 24? Okay, maybe you might have to go back to your list here. I'm going to put that list. There it is. 1, 8. 8. 8 is in 24. So this is the cube root of 8 times 3. Now 3 is not a perfect cube, but 8 is. So that's the cube root of 8 times the cube root of 3. So this is 2 cube root 3. Now I'm always careful when I write these. I make sure that that 3 is definitely closer to this radical bracket than it is to that 2. I don't want people to think this is 2 cubed times the square root of 3. It's not. It's 2 times the cube root of 3. Sometimes I even make this a little exaggerated just to make sure it's kind of holding on to my 3. Nothing worse in math than when you're misinterpreted and misunderstood. All right, number 5. Simplify this thing. Well, again, I think the biggest perfect cube in that number might be an 8, because after 8 it's 27. After 27 it's 64. Those two numbers definitely don't go into 96. So it is the cube root of 8 times 12. 12 doesn't have any perfect cubes in it. 8 is a perfect cube. So again, this is 2 times the cube root of 12. Cube root of 108. This doesn't have an 8 in it, but you know what it has in it? It has a 27. You know how I know that? 9 goes into 108, and another 3 goes into that afterwards. So it's actually a cube root of 27 times 4, which is 3 cube root 4. All right, time for a definition here. A little more note writing. Sorry, folks. Entire radicals are numbers where the total, entire, if you like, value of the number is contained under the radical symbol, also known again as the root symbol. For example, the square root of 20, or the cube root of 250, or the square root of 3x squared y. Eventually we're doing these with algebra too. Okay, so that's an entire radical. The whole thing is under the radical sign. A mixed radical, as you might guess, is kind of the stuff we were doing here. It is a number that has a rational factor and an irrational radical factor. So examples would be something like 2 root 5, 5 cube root 2, and x square root 3y. Get it? They have a rational part and an irrational part. And in case, what do you notice about those three numbers? These are actually the exact same numbers that I just used in both examples. This simplifies to that, this simplifies to that, and this actually does simplify to that. We'll get more into doing this with algebra once we've played with some numbers for a little bit. So moving on to example 4. Let me get my papers organized here. Or sorry, example 4. That was example 7. That's where I want to be. I'm on example 7. All right. A little bit of typo happened here. We're going to have to do some fixing here. It says write the following as a mixed radical. Well, that is a mixed radical, so let's fix that. That's supposed to say write the following mixed radical as an entire radical. Okay, and actually all of the instructions on this page should say that. As an entire. Okay, so fix all the instructions for me. So 4 root 3 I can think of as, okay, so I'm going backwards from what I was doing to simplify it now. So I want this 4 to go under the radical bracket. So what's square rooted makes 4? I actually just asked the same question as what's the square of 4? So this is like saying root 16 times root 3, which is root 48. Let's try that again. This is like saying the square root of 49 times the square root of 3. And okay, I got to do a little mental math here. 3 50s would be 150, so 150 less 1 3 is 147. Somebody can double check my mental math on that. And for this one, 5 root 2 is like saying the root of 25 times the root of 2, which is the root of 50. So notice these simplify to those, but those are mixed radicals, and these guys are entire radicals. Depending on your situation, sometimes you want one thing, sometimes you might want the other. All right, example 10, again, fix the instructions, write the following mixed radical as an entire. As an entire, sorry, bit of a typo there. All right, so now 2 has to go under this cube root radical. So that means I have to think of what number 2 becomes when you cube it. Well, the cube root of 8 is 2. And we're timesing that by the cube root of 4. So we're actually looking at the cube root of 32. What number does 3 become when you cube it? Well, it becomes 27. So 3 is the cube root of 27. I can write it that way. And I can combine those two things using my multiplication rule. So that's the cube root of 3 27s is, let me think, 81, right? There we go. Again, somebody check my mental math. All right. So that's the examples up to 11. In your new booklet, and that takes us to the end of the 4.3 lesson. Okay, so you'll be getting an assignment on this stuff. Good luck. Practice hard.